and interesting talks. So next up, I would like to introduce our speaker, Dr. Kristoffer, from the Department of Marine Sciences at the University of Gothenburg in Sweden. Dr. Kristoffer's expertise in the sustainable production of seaweeds is pushing the boundaries of what we know about seaweed cultivation. Dr. Kristoffer's journey into seaweed research began at a salmon aquaculture farm in Norway, where he first encountered the potential of seaweed species to address nutrient pollution. This early experience ignited a passion for seaweeds and led him to explore innovative ways to enhance their cultivation. Dr. Kristoffer's research focused on investigating seaweeds as a sustainable protein source and exploring novel ways to improve cultivation conditions. Specifically, he examined the use of food production process waters to optimize seaweed growth. In addition to his academic pursuits, Dr. Kristoffer is an enthusiastic diver. He seamlessly integrates his love for diving into his research, often collecting seaweeds for experimental studies directly from the marine environment. This would have given him a valuable hands-on insights into seaweed cultivation. Dr. Kristoffer's innovative approach on Ulva production promises to offer us a fresh perspective on optimizing land-based cultivation systems. Dr. Kristoffer, please feel free to share your screen and start.
Thank you so much. Thank you for that nice presentation. We'll see if I manage to share this. Okay. It's saying it's processing, so just a second. Okay, so do you see the presentation now in presentation mode?
Perfect.
Perfect. All right, so thank you. Thank you for inviting me to give a talk here at this workshop. I'm very glad to be here. In my presentation, I will talk about innovative cultivation methods for Ulva, Ulva fenestrata, and this is most of my work from my PhD thesis that I will show you here. But first, I thought there was a bit of that in the introduction already, but so a little bit of background why I started working with seaweeds. So I started doing my master's thesis at the salmon aquaculture farm. I was interested in sustainable aquaculture, and I mostly focused on the fish. That was my idea. And then, as David talked about a little bit before in the previous presentation, there was this concept of IMTA to use the seaweeds in co-cultivation with the salmon farm. So this is the salmon farm I worked at, and here you can see these are the tanks where I put in seaweeds, and we led the water from the fish tanks directly into these seaweed tanks. And here you can see a picture of me. So this is with Saccharina, so we were cultivating kelp, the Saccharina. And I mean, I didn't have a lot of experience with seaweeds before, but this was the seaweeds after 30 days. So my mind was kind of blown away that something can actually grow this fast in just a month. And for at least what I know, terrestrial plants, there's nothing in comparison to these growth rates. So this is really where my interest in seaweeds really kicked off. So for my PhD thesis, I wanted to see if we could use this concept also, but for other types of process water or wastewater from other industries, because in Sweden, we don't have a lot of fish aquaculture, but what we have is a lot of other industries that produces a lot of water. So here we can see some examples from, for example, fishing industry. When they land the fish, they have to store the fish in different types of the salt waters. This is a land-based salmon farm. We have processing of shrimps, for example, and other types of industries. So they use a lot of waters, but yeah, these waters are very high in nutrients. But today, by the companies, they're being treated as waste. So I mean, there is a high loss of nutrients in these waters, and there's also a cost for these companies to actually clean these waters. So there is an incentive to try to valorize these waters, also coming from these industries. Um, yeah, so this is just one example of a herring producer. They produce 12,000 tons of herring every year, which gives them a lot of water, and they spent approximately 180,000 US dollar every year for water treatment of this. So, I mean, they are interested to see if they could valorize these waters. Um, yeah, and as I showed in the first couple of slides there with the kelp, seaweeds they grow faster and they also accumulate nitrogen, which they then metabolize to proteins when they're cultivated in these in nutrient-rich waters. So, I mean, that's lucky for us because then we can use these waters as a growth media. Um, So here are two of the types of process waters that I've been working quite a lot with. So it's coming from herring. In Sweden, we love to eat herring in different forms. So there is this water that I refer to as tub water, which is from pre-processing of whole herring. So then they are stored in these tubs that you can see here. And then it's also saturated salt brine from when we maturate the herring fillets. And let's see if I can see here. So this is just a characterization of these waters to show you the amount of ammonium that is in these waters. So this is in millimolar. So it's in ammonium here. You can see that in seawater from where I work, this is the concentration of ammonium. So you can see that it's a really high concentration of ammonium in these waters. So this means that we have to dilute the waters quite a lot to not shock the seaweeds. Yeah, I will try to move here so you can see. So we dilute them by quite a lot to reach the ammonium concentration that we want to use in our experiments. And let's see if, yeah, maybe I can't. This is supposed to be a video, but it seems like I can't start it. But so, I mean, here you see a seaweed tank of Ulva, and you can see this how much process water I add. So we use it more of like a fertilizer for the seaweed, and this is based on what we see here when we increase the ammonium concentration. We have this rapid increase in crude protein content of the seaweed, but once we come up to a certain point, it doesn't add much for the crude protein content or growth rate, at least. Um, so that's why we diluted this much. But of course, if you would want to look into more of a bioremediation purpose, you would use more of the water to clean it. So why are we then working with Ulva? Well, we think it's a very nice species to work with because it's globally distributed, and it's a very opportunistic species that have high growth rates already. You can have it at high stocking densities, and it's also tolerant. It's tolerant towards very environmental factors like different salinities, temperatures, nutrient concentrations, which makes it a very good species to work with if you want to use these process waters. And then it works well in both sea-based and land-based cultivation. And it's also very interesting for the food industry, pharmaceuticals and feedstock, for example. It has a composition of, yeah, it's very high quality proteins and yeah, other biochemicals. And then when I started my PhD thesis, I did a meta-analysis where I screened the studies out there that has been used different types of wastewaters. And it was very clear that green seaweed species are very good to use in these types of settings. So this is the results from one study I did where we have, so you can see here we have the yellow bars. They are just when the seaweed is cultivated in plain seawater. And then we have these two different types of process waters, so sal and tub that I showed you before. I mean, so you can clearly see that they're growing much better when they're growing in the process water. It's a huge increase. But what I think is most interesting from a food perspective is if we look at the protein content and we talk about this, that we are going to change the protein sources that we eat and stuff like that. So then this is very interesting to see that we can actually increase the crude protein content in the seaweeds from around 12% in the seawater to over 30% by just cultivating them in these waters for 14 days. So that was very nice results. And what we also saw was that they had the protein had a very high content of essential amino acids, comparable to eggs, for example. And we also saw that all of the essential amino acids increased. So, for example, methionine and lysine, which is generally perceived in vegetable protein sources, was not a limiting factor anymore. So that was very nice to see also. But then, of course, if you want to eat it, we want to make sure that it's also a safe product to eat. And we had some concerns because, I mean, herring, they can contain quite a lot of different heavy metals. So we wanted to make sure that the seaweeds didn't actually take up any heavy metals from the herring. So we looked into inorganic arsenic, mercury, lead, and cadmium. So this is just a calculation I did because I think it's a bit easier to understand than just showing the values. But this is a calculation of how much seaweed cultivated in these process waters can we eat every day without exceeding the recommended daily dose set by the European Food Safety Authority. So here you can see that we can eat, I mean, this is in wet weight, so we can eat 0.7 kilograms of wet weight or 1.1 kilograms of wet weight of the seaweed cultivated in the tub water every day without exceeding these references value. And I mean, that is really a lot. I don't know if that tells you that much, but it's really, really a lot of seaweed. And if we compare it to how much they eat in for example, Japan, China, or South Korea, it's around 50 grams every day. So we can eat quite a lot of more than that. And of course, this also assumes that all of the heavy metals in the biomass is actually bioavailable for us. So meaning that we will actually take up everything of it. So, all right. So now I'm gonna jump into another aspect to see how we can use this process water as a post-harvest step. So here in Sweden, where I work, up here, close to the Norwegian border, we also have this sea farm of Ulva, where we cultivate the Ulva like this on long lines that David talked about before. And this is some work done by one of my colleagues, Sophie Steinhagen, where she showed that the harvest time really affects the biochemical composition of the seaweed and also the growth of the seaweed. So this is a cultivation period of over the year here. So we have working with a cold water species. So we like to grow it in the beginning of the year when the water is not too warm. So we can clearly see here that when the temperature of the water increases, this will also happen with the dry weight will increase to a certain point, but then it will go down. And for proteins, if we're interested in proteins, we have a high protein content in the beginning of the year, but if we let the seaweeds be out in the ocean for longer, it will quickly go down. So, I mean, there's a difference from around 5% protein to 20% protein, depending on when we harvested it. And you can also see on the biomass that it looks much greener in the beginning. So we wanted to see if we could extend this season by a post-harvest cultivation. Um, so we harvest it when they have a low protein content, but we have a lot of biomass. And then we wanted to see if we can put them in tanks and increase the protein to what it was before. So we harvested it here when we had the most biomass, but here when the protein content was very low. So when we harvested them in May, they had around 4% protein content and they were very pale. But after just 14 days in these tanks, they were back to their natural protein content when they had the highest content. So it was also very nice results. See. Yeah. And then we also wanted to see, just out of curiosity, really, if we could increase the protein content even further. So we harvested them when they had their already natural highest protein content. So in the end of February. So here we have the start. They had 21% when we harvested them in February. Then we cultivate them in this PES, which is a commercially available seaweed cultivation media. And then in this tub process water. And we can see that the tub process water, it outperforms this commercial media. And we managed to get the crude protein content of 37%, which is, to my knowledge, the highest one I've seen, at least published. But it's important to note that this is the crude protein content, and so it's an estimation of the protein content. But what was nice was that we also saw that there was no fish allergens in these biomass, meaning that even if we cultivate the seaweeds in fish wastewater, people that are allergic to fish can still eat it. So that was some nice results to see. And then we've done some sensory analysis on this to see if this wastewater affects the sensory aspects of the biomass. And from this panel, they tested the biomass, and what they really saw was the difference in color. So you can clearly also see by just looking at the pictures that the more olive green is when they have a higher protein content and they are cultivated in this tub water, compared to this more pale green when they are just plain seawater. So now I'm just gonna go into a little bit of a side project with this, but I think it's a nice way to show what can be farmers can actually use. So I mean, this color difference here is I mean, nitrogen is a major part of the chlorophyll molecule. So when we have more nitrogen, which means we have more protein, they get greener. So this is what you can see here in these pictures. So I went out for a cultivation season and collected seaweed over this whole cultivation period that I showed you before. So I had high protein content and low protein content. And then I took photos of this biomass, and then I extracted the red, green, and blue values of this. And this is just a way for like a display to show the colors. So we saw this really nice correlation where if we have a higher nitrogen content, it also has a lower value of these red, green, and blue values. And this means that we could use this to estimate, just by taking a photo of the seaweed, how much nitrogen content or crude protein content it actually has. So we developed this website, seaweednitrogen.com, which I realized afterwards it sounds more like we're making TNT or something. But here you can just take a photo. If this is for Ulva only, but this should work with other species as well. So you take a photo of your Ulva fenestrata, you upload it, and you remove the background with this here, and then you get out the results of how much nitrogen does this seaweed contain. And then you can convert that to protein. So I think this is a nice, rapid and cost-efficient method to estimate the nitrogen. So an overall conclusion, I mean, Ulva has the potential to become a very interesting protein source, I think. And cultivation in this process water increases growth and crude protein content. But yeah, these high protein levels are very important, I think, for the downstream application, because I think we will hear more about this maybe tomorrow in later sessions about protein extractions and bioavailability of proteins. So it's important to have a high protein content in the biomass already. And then we get this loop where nutrients from industries that are currently discarded can then be turned into a protein-rich biomass through the seaweed cultivation. So with that, thank you all for listening. And of course, this was a work of many. So here you can see some of the people involved in this work and the different companies that we've been working with. So thank you so much.
Great. Thank you so much, Dr. Stedt. Really fascinating to see waste valorization being used for land cultivation. So certainly very, very interesting.